Then comes a subtle thing. We are nearing the boundary of measure theory. Measure theory cannot do everything. There are little tiny things where we have problems. So the question is now, okay, is this okay for all A in this set? And that's of course what we want this to be, that this should be okay for every set here. And that's where we need a warning. Yes, if these mu1 and mu2 are not pathological. Mu1 and mu2, we need a really tiny amount of regularity. If mu1 and mu2 are sigma finite, what does sigma finite mean? It means that there exist some sets. Let's do a definition. Mu is sigma finite. Well, if mu is a finite measure, then it's sigma finite as well. But you can have sigma finite if you are not too infinite, namely, if there exists A1, A2, which are measurable sets, and they grow towards the full set. Let's call it S. And each of these sets is finite. So sigma finite means actually that mu of S, this could be infinite, but you could still write it as a limit of some finite measure thing. So if A and are increasing to S, and then you could have this measure of the full space as limit of something, and all of these things are finite here. So these need to be finite for this to work. That's the restriction of Fubini and Tonelli's theory. Let's clean this up now. And maybe we could write it as a theorem. If mu1, mu2 are sigma finite, then there exists a unique measure, which we call mu1 times mu2, such that mu1 A1 for boxes, sorry, the unique measure, what it assigns to a box, is equal to product of these. And we need to say that this unique measure on the product sigma algebra for all A1 in S1 and A2 in S2. That's the theorem about the existence of a product measure. So product measures always exist for sigma finite measures. The existence is proved by defining the measure in this way, and then proving that yes, it's a well-defined map, and that we already discussed that this is a well-defined. And then we need to verify. What else do we need to verify? Well, it matches with the boxes. So what is actually there? still to do. We have a good definition here. What we need to do is that we need to verify that this is a measure. Yeah. What do we need of a measure? The simple thing first is to look, okay, what's the measure of an empty set? If we plug in empty set here, then you know that the integral of an empty set is 0. So then we have integral S1, integral S2. We are integrating 0 with first mu2 and then with mu1. Well, integral of 0 is 0 inside and then on the outside as well. So empty set has a measure 0 as it should be. Should have. What else? So let's put it down there. That was the trivial part of the proof. The second part is that we need to prove that it's countably additive. So let's take B1, B2, etc. to be disjoint. And then what we need to do is that we need to show that this for disjoint unions, we get the sum here. That's what we need to do. So to do this, let's define UN as the union up to N. And then let's recall that, okay, if we have a disjoint here, disjoint, or everything, so then the indicator of disjoint sets is actually the sum of these indicators. So that's what we get for disjoint sets. And then now we can calculate what is the product measure of UN. So this would be finite additivity. And by definition, it was the integral S1, S2, indicator UN, because that's how we define the integrals, and then inner integral, outer integral this way. And now we have here, we have a sum here. So we take the sum in front and in front. So it goes in front both ways and it comes to the really front. And then we have S1, S2 integrals there. In indicator BK, inner integral mu2, outer integral mu1. And if you recognize what is this here, this is just the product measure mu2, mu1, mu2 of BK. So now we know that things work well for finite disjoint unions here. Okay. What about then for the full set B, which is now the union from K from 1 to infinity of BK? Now we know that these sets UN, they get bigger and bigger when you increase N, and then they increase to B. Then also it follows that this indicator function, they grow pointwise to the indicator of B. Then what do? We want to calculate what's the product measure of the infinite union, this B. Let's recall the definition. We had this outer integral, inner integral, indicator B here. And remember, these are done one by one. Okay, now what? We know that there's pointwise increasing limit of UN, indicator UN to indicator B. So especially we know that for every S1, S2 pair, these numbers increase to the indicator of B, S1, S2. And what does it mean? Take any pair of S1 and S2, any pair of points, and look at this number sequence. So it increases to the indicator here. Then it's also true if you fix S1. So fix this one. Now we have function of S2 and we have a function sequence of S2 variable and they increase. This is as S1 is fixed, so it's a function of S2. This is the variable that we think as a variable, and we have a function sequence increasing in that variable. Then we use the monotone convergence theorem. We have non-negative increasing function limits. That's why what we have here, what is there is a pointwise increasing limit of functions indicator un. In terms of variable S2, we bring the limit outside of this integral. So we take limit there. And we have integral there of this un integrated with mu2, and then the outer integral. Again, these are now, remember S1 is fixed and hidden there, so then this is kind of some function of S1 now. It's a number which depends on S1. It also depends on n because n is there. So these are increasing in n again. Let me actually take this away. It's maybe easier to think as a sketch here. These are increasing again as function of S1 to the indicator of this integral. That's what you can check. And again, you have a monotone limit of functions and you integrate. So you use again the monotone convergence theorem. So you use the monotone convergence theorem of, that was the other important continuity of the integral. So you can bring the limit in front of the second integral as well. And then we have S1, S2 indicator un this way. And that is, what is that? We learned before and that for un, this was the sum of these bk's. So what is there? We have a limit n to infinity, sum k from 1 to n, mu1, mu2 measure of set bk. And non-negative things, we are summing n to infinity, so that's of course by definition of an infinite sum of bk. End of the story about this. So that actually proves that this one was the infinite union of disjoint. It's actually infinite sum of the sets. We conclude with this derivation that yes, this is a measure. And that's why it is a product measure. And that's kind of part of this theorem. Do you have questions here? I do. My question is that we needed the assumption of the sigma finite. So where did we use the sigma finite assumption? In this part of the proof, I think we didn't use it anywhere. No. We didn't use the sigma finiteness there anyway. So actually, I think that part of the proof should work without the sigma finiteness. We didn't prove that this is the unique measure with this property. So for the uniqueness, that's where the monotone class and then the kind of that you can change these integrals. So that's where you need the sigma finiteness.